Welcome to NASA Launchpad. I'm your host, Audrey Staples. Question: which doesn't belong in this list? Ocean waves, sound waves, microwaves, seismic waves, radio waves, electromagnetic waves. Yeah, trick question. They all fit in the list because they're all waves. Okay, maybe the image of the microwave doesn't fit, but microwaves as well as radio waves are part of the electromagnetic spectrum. Why are waves so important? Well, surfing's pretty boring without them. And think about it. No sound waves, no sound. No light waves, you couldn't see anything. No microwaves, don't want to go there. But just what is a wave anyway? Waves are disturbances that transfer energy from place to place. Many waves require something to travel through. Water waves travel along the surface of water, and sound waves travel through the air. We can even make a wave travel along a rope. Try this. Look what happens when I tie this rope to the doorknob, and then move it up and down quickly. Whatever the wave is traveling through is called the medium. Gases, such as air, liquids, such as water, and solids, like our rope, can all act as medium. Any wave that needs a medium is called a mechanical wave. The amazing thing about waves is that although they travel through the medium, they don't carry the medium with them. So what causes waves? Simple. Waves are created when any source of energy causes a medium to vibrate, or move back and forth, or up and down repeatedly. Moving objects have energy. That energy is transferred to the nearest medium, and suddenly you have a wave. The wave we created with the rope is a transverse wave, the same kind of wave found in the electromagnetic spectrum. As a transverse wave moves in one direction, the particles of the medium move across the direction of the wave at a right angle. Some parts of the wave are high, called crest, and some parts of the wave are low, called trough. The measurable distance from one crest to another is the wavelength. Let's watch Canadian Space Agency astronaut Bob Thirsk on the International Space Station as he demos a different kind of wave, a longitudinal wave.
So let's look at the speed of a wave and how tension affects it. So I'll pull the slinky about 10 centimeters apart, not very tense, and release it. See how fast the wave is moving. Brisk, but not too fast. Let's try that again. Here we go. Okay, now let me stretch it out a little bit more and put some tension onto the slinky, and watch the speed now. See the pulse wave move? Quite a bit faster. Let's try that again. Slow. Fast. So the tension affects the speed of the wave. Let's look at the reflection of a wave. I'll pull the slinky apart, and when I release it with this hand here, I want you to watch how the wave travels down, stops at the fixed end, and then reflects back in the opposite direction. Here we go. See how it reflects back and forth? Try it again. I'll hold this hand fixed, let go the slinky, and you can see how it reflects back off the fixed end and back to the initiating hand.
How did those waves compare to the waves we created with rope? Longitudinal waves move the particles of the medium parallel to the direction the wave is traveling. The coils in the spring move back and forth in the same direction as the wave travels. The parts where the waves are close together are called compression. The parts where the coils are spread out are called rarefaction. After the wave passes, each part of the spring returns to the position where it started.
Standing waves are waves that don't appear to move at all, and in fact the nodal point stays fixed. Let's try, see if we can get a one-node standing wave going here. There we go. That one's pretty easy. So the nodal points are at the fixed ends of the slinky.
Surface waves, like those that occur at the surface of the ocean where water and air meet, are combinations of transverse and longitudinal waves. The water moves up and down, like our rope. But the water also moves back and forth, like the coils in the spring. Unlike the coils, though, the water does not compress. Instead, the up and down and back and forth movements combine to make the particles of water move in a circle, creating the circular motion of surface waves. You could try these same demonstrations in your classroom or at home to help you learn more about waves. But why would astronauts on board the International Space Station need to understand more about waves? In the microgravity environment of the ISS, tiny vibrations or disturbances, even those caused by crew exercise, can upset sensitive science experiments. Special shock absorbers, such as the active rock isolation system, act as a buffer between the experiment and the vibrations. Other equipment on board the ISS collects data and measures vibrations, so future hardware developers can design equipment to operate more efficiently in the microgravity laboratory. Now that would be a cool job, designing a shock absorber used in space. That's it for now. I'm Audrey Staples. Catch you next time on NASA Launchpad.